angular matter has inertia which opposes any change in its velocity or direction. Air moving rapidly past an object with sharp corners tends to continue its motion past the object. But a low pressure area is thus created, and the difference in pressure, or pressure gradient, changes the direction of the airstream, bending it in toward the plate, creating whirls and turbulence. Turbulence is one of the two principal factors opposing the useful employment of airfoil. The other parasite factor is termed skin friction, or surface resistance to relative motion. Highly magnified, the best possible surface has irregularities from which air particles rebound into the airstream, colliding with other particles, setting up friction and interfering with these flows, thereby opposing the relative motion. This opposition can never be eliminated, but can only be reduced by using the smoothest surfaces possible. An airstream can be seen and studied by means of an optical device through which we here see warm air rising above an electric wire. Replacing the electrically heated wire by a spark gap produces an effect which aids visualization. The actual airspeed is much higher than it seems. The apparent flow motion is a stroboscopic effect. Placing a flat plate in the visible stream, we observe a physical demonstration of the turbulence previously shown graphically. Turbulence in the wake on the upper surface of the plate is now made visible by means of fine wires electrically heated. The symbol alpha indicates the angle of attack. The seemingly reduced airspeed is now about 1/100th of the actual airspeed. Air flows past the plate above and below, leaving a wide turbulent wake behind. Some air pours into this wake from above and below. The turbulent air on the back of the plate actually flows forward up the plate. It does not matter whether the plate is still and the air moves, or vice versa. The airflow pattern moves with the plate. At a small angle of attack, turbulence practically disappears, and the wake becomes very narrow. With increasing angle of attack, turbulence increases, and the wake widens. The stalling angle is the angle at which the flow pattern suddenly changes, extending the area of turbulence over the whole plate right up to the leading edge. Reverse flow up the plate is characteristic of the stall. The plate is deflecting the air downwards and retarding its forward flow slightly. In doing so, it gets an exactly equal and opposite reaction from the air, represented by the arrow acting upwards and backwards. It is obvious that if this plate were left loose, it would be blown upwards and backwards before it dropped. The resultant air force increases as the angle of attack is increased. It reaches a maximum when the plane of the plate is perpendicular to the direction of airflow. As we increase the angle of attack from 0, lift increases at first and then decreases. The drag goes on increasing. The resultant air force is now all drag. Turbulence is affected not only by the attitude of an object, but also by its shape. The turbulence due to this plate is decreased by putting a nose on the plate without decreasing its width. By adding a short tail, we decrease the turbulence only slightly. A longer tail shrinks the wake to very small dimensions. The drag of the streamlined plate is only a small fraction of what it was. Here we see the airflow past a body of circular section. Although this ball presents no sharp angles, it creates considerable turbulence. Compare this wake with that of a streamlined shape having the same cross-sectional area. Going back to the flat plate, we have seen how inertia carries the air past the plate, leaving a partial vacuum. Air particles nearest the partial vacuum are impelled in toward it on a spiral path, which sweeps them again outward from the plate into collision with the main airstream, bending it outward in the manner which we observed in the actual photograph. By adding a curved approach to the leading edge, abrupt change of direction is prevented. The airstream nearest the leading edge remains in contact with the surface, and a more orderly flow takes place. The actual airstream verifies our conclusion as to the effect of the curved leading edge. Although some turbulence still exists, the airflow over this cambered plate is smooth up to the higher angles of attack. It is, of course, necessary to brace the plate in order that the structure may be strong enough to carry the load for which it is intended. Heavy spars, here shown in cross-section, extend the full length of the wing and give it the necessary strength. Then, streamlining these spars, we have an airfoil section. Observe the narrow wake and the absence of turbulence at moderate angles of attack as compared with a plate. As the angle of attack is increased, turbulence creeps forward from the trailing edge, and the wake again becomes wide. The symbol alpha here denotes stalling angle. Observe the rapid change in airflow pattern and the formation of a wide turbulent wake when stalled. As in the flat plate, lift and drag increase with increasing angle of attack. The apparent speed is further reduced by slow motion. The angle of attack is being increased above the stall. Turbulent air at the trailing edge starts flowing forward up the back of the airfoil, and the smooth or laminar airflow leaves the top surface. Air is obviously flowing into the wake from above and below. In the case of the plate streamlined by the addition of a nose and tail, we observed the greatly decreased turbulence obtained by adding a longer tail. The essential difference between these two objects, which is closely related to turbulence produced, is the ratio of length to thickness. This is called the fineness ratio. With a given cross-sectional area of an airfoil, a small fineness ratio favors increased turbulence and decreases skin friction. Whereas an abnormally large fineness ratio would decrease turbulence at the expense of increased skin friction due to its larger surface. A compromise based on these and other design considerations appears to be advantageous. A thick airfoil has a relatively large drag at a low angle of attack due to direct impact of the air on its thick leading edge. At larger angle of attack, the thick airfoil has less turbulence and more lift than a thin one, owing to its more gradual change in direction of the airstream just behind the leading edge. Airfoils like these, with sharp curvature at the leading edge, present their most favorable attitude at large angles of attack. They are best adapted for heavy lifting airplanes. At low angles of attack, turbulence along the lower surface causes excessive drag. We have observed the aerodynamic characteristics of normal airfoils whose maximum thickness occurs about 1/3 of its length back of the leading edge. If the position of maximum thickness is too far forward, the nose is too blunt and excessive turbulence occurs at practically all angles of attack. There is direct impact of more air on the nose and too rapid change of direction at the point of maximum thickness. Airfoil sections such as this, with maximum thickness well toward the rear, have until recently been considered inefficient owing to excessive burbling caused by abrupt curvature at the point of maximum thickness. Recent tests have indicated points in favor of a section such as this for very high speeds and consequent small angles of attack. Decreased drag results from the narrow leading edge and from the particular shape having maximum thickness at about midsection of the airfoil. The relatively low lift at large angles of attack is of minor importance in the fastest airplanes. This is what may happen when ice forms on the leading edge of the wing. The airflow has broken away from the surface, leaving a wide, turbulent wake. Streamlining has become increasingly important in the attainment of speeds now necessary. Cockpits are enclosed in sliding canopies. Alighting gears are either streamlined to reduce wind resistance or are retractable. The junction of wing and fuselage surfaces is filleted to effect a gradual curvature rather than an abrupt angle. A streamlined engine nacelle without the engine offers small opposition to airflow. But with a radial engine installed, the turbulence and the very wide wake indicate a considerable drag. A ring which conducts air over the cylinders limits the area of turbulence, reduces the wake, and improves performance. This is the cowling developed by the National Advisory Committee for Aeronautics to reduce the turbulence due to radial engines. Liquid-cooled engines simplify the streamlining problem since they do not require a stream of air over the cylinders.